Okay, so we'll explain first of all what this term similarity means. It's kind of a vague term, but if you read the learning intention success criteria, it'll give you an idea. So we're going to be able to use a scale factor for similar shape calculations, identifying the features of a similar shape, so what makes a shape or two shapes similar in mathematical terms, and finding the scale factor for similar shapes and using it to find missing lengths, areas, or volumes. That's what this topic is all about. Okay, so generally, one of the easier topics that is more easier to get your head around. We're going to spend probably just this week doing it, and that should be enough time. Okay, so there's a few things that I want you to copy down first of all. So I do want you to copy the first couple of lines here. So two shapes are said to be similar if they are the same basic shape but a different size. Okay, so two similar shapes, they must have, in order to be similar in mathematical terms, the corresponding angles the same. So, you know, if I have an angle in this corner in my smaller shape, is it the same angle in the bigger shape in the same corner? That's one of the rules. And the second rule is their lengths must be in proportion to each other. So if you've made it bigger or made it smaller, every single length needs to have increased or decreased by the same proportion. These are two important things. I actually want you to copy what's on this screen just now, please. I don't want you to copy the rest of it, but what's on this screen just now, can you please copy? So spend just 30 seconds doing that, please. So mathematically similar shapes. So it's all about shapes, and it's all about basically shapes that have got bigger or smaller. Okay, that's all we're really doing here. They are mathematically similar if their corresponding angles are equal and if their lengths are in proportion to each other. Okay, so kind of think of your head of something like Russian dolls. It's kind of an idea of what we're going for here. Same shape, but proportionally bigger or smaller. Okay, so that's all the copying I want you to do just now. You can just, I'm going to keep this on the screen if you're not yet done, don't worry. But I don't want you to copy these shapes, I just want you to look at what they say. So I've kind of done a little example here of what I'm talking about. So if we have rectangle A and rectangle B, these rectangles are mathematically similar. They are similar because in the larger B shape, the angles are still all 90 degrees. The corresponding angles haven't changed. So this bottom left angle is still 90 and this bottom left angle is still 90 in B. Okay, so the corresponding angles are the same. And if you look at the lengths of the sides, that is 3 centimeters by 4 centimeters. And in rectangle B is 6 centimeters by 8 centimeters. So both of those lengths have been proportioned up by a factor of 2. They've both been doubled, right? So because they've both been multiplied by the same number, it means that they are in proportion, which means that the shapes are similar, mathematically similar. Okay, so in this case, B is an enlargement of the other. It has been scaled up by a scale factor of 2. Okay, so you don't have to copy that, but hopefully that makes enough sense. And I've got a further kind of example to show you of what are not similar shapes. So if we look at these two, I'm starting with a parallelogram in C, and I've got these angles here, 70, 70, 110, 110. And in shape D, it looks pretty similar, but the angles have changed. So the corresponding angles, which in these cases would be, you know, the red ones, they are no longer the exact same. Okay, that is no longer 70, and the corresponding angles on the other corners are no longer 110. Therefore, it is not a similar shape because the corresponding angles are not the same. They've changed the shape slightly. Okay, so that's what you need to think of. Are the angles the same? And really, in our case, we're just looking at the lengths of the sides. We don't deal too much with angles. Okay, so before we get on to the actual printed notes, I just wanted to show you a few examples. So I don't want you to copy these down, so just watch me go through these, and this should hopefully be a good introduction here. Okay, so what I've got for you just now is two shapes. They are trapeziums, okay, and I have the corresponding angles marked on, and I have the lengths of the sides marked on. Now it says here that both trapezia, they are similar shapes because their corresponding angles are equal, they're still the same. And if you look at the lengths of all the sides, again, they have all been multiplied by 2. So because they've been multiplied by the same number, it means they are in proportion, which means that they are similar shapes. So the question would be is basically, what is the scale factor here? The factor is how much all the sides have been multiplied up by. Now, it's not rocket science. In the new shape, all we have to do is we literally just pick any of the corresponding sides. So the easiest one is along the bottom here. We can say that in the new shape it's 12, in the old shape it's 6. So the scale factor is the length in the new shape divided by the length in the old shape, which is 12 divided by 6, which is just an answer of 2. So we would say that every side has been scaled up by a factor of 2, right? And that calculation would have worked the same if we'd chosen any of the sides there. So if we'd chosen the top lengths, we would have said 8 divided by 4, which also would have given 2. 6 divided by 3 also would have given 2. Okay, so as long as you choose the same corresponding side in each shape, you're going to get the scale factor. Right, I'll show you this again in this shape. So this is kind of like I don't know, kind of looks like one of those power station chimneys. And we're told that they're similar. So we don't really need to worry about the angles here. We're told that they are similar. What we have to do is figure out what has the second shape been enlarged by and calculate the length of side X. So again, just watch me do this one. We're going to do a similar example from our actual notes in a wee second. So we look at the sides that we're given. We're given this horizontal side and we're given the height in the smaller one. And we are told the horizontal side in the bigger one, but we're trying to find the height of the new shape. So what we are going to do is we're trying to find the scale factor, which when we're dealing with lengths, we call the length scale factor. Again, just watch me do this just now. The length scale factor, which we are going to shorten to LSF. All we do is we take the new length and we divide it by the old length. So we have to pick the sides of the information we're given. Now we're not given the information in the new shape with the 6 height there, so we can't use that in this fraction. We have to use the 2 that we actually have numbers for. So it is 10 divided by 4, which it will often be a fraction when we do these questions, so I need to simplify that fraction in its simplest form. So the length scale factor is 10 divided by 4, which we would simplify to 5 over 2. Now that's part A. What is the length scale factor? So the length scale factor is 5 over 2. So it's increased by 5 halves, basically. So in question B, it would be calculate the length of side X. Now to get the actual length of the new length, or the new height, let's call it, all you do is you take your length scale factor and you multiply it by the corresponding height of the smaller one. So in this case, all we would do is do 5 over 2 times 6, and all I have to do is work out what that is. So multiply the top things together, 30 divided by 2, so it's going to be 15 centimetres is that new height. Okay, so we're finding what the scale factor is, and then we're just taking that scale factor and multiplying it by the other length. That's pretty much all we're doing here. Let's try some for our own. Okay, and I do want us to draw these shapes out, draw the pictures, and do the working just now. So we're going to jump to our actual notes. So what I do want you to copy down is what's in this grey box. So start doing it now. So the formula for the scale factor, which is what I kind of wrote down in the last one. So the scale factor, length scale factor, is the length in the new shape divided by the length in the old shape. And how we actually figure out that length, that was like part A, how we figure out the length. Part B was the length scale factor times by the old length. That's exactly what you've just watched me do. So copy down what's in that box, please. You need those two formulas. Okay, so we're going to work first of all with the length scale factor, which is where we use the scale factor to find the length. Then we are going to progress onto area scale factor and then onto volume scale factor. But right now, all we need to worry about is the length. Oops, sorry. So copy down what's in that box, and then I want you to draw example 1A. So I have two picture frames, and I am told that they are mathematically similar. So the corresponding angles are the same. We don't need to worry about that. Okay. What I do need to worry about is drawing these two shapes, writing on the information that I'm given, and then what I'm trying to do is find out what this side X is. So you can see that from the bigger frame to the smaller frame. So our shape has been reduced, it's been made smaller. So I need to figure out what is that scale factor that has reduced the shape using the two corresponding sides I'm given, and then times it by the other length to find X. Okay, so there's two stages to this. First stage is find out what the length scale factor is. So I'll do this in bullet points. Find what the length scale factor is. So the length scale factor is going to be, So find the length scale factor, that's the first one, and then use that to calculate X. Okay, so the length scale factor is quite simply it's always the new length, or the one with the unknown, divided by the one in the shape that I'm given at the start. So it is always new length divided by old length. Okay, and this has to be only using the two that I am given. Okay, I'm given numbers for. So new length divided by old length. So that's going to be, in the new shape, I'm going to have to use these horizontal sides at the bottom because that's the only two sides that I have both numbers for. So it's going to be 10 divided by 25. Now I will have to always simplify that fraction fully. So they're both divisible by 5, so that's going to be 2 over 5. Okay, so just a bit of kind of theory. If the shape is getting smaller, it has to be multiplied by a fraction that has a value of less than 1. If the shape is going to get bigger, the fraction is going to be greater than 1, i.e. a top-heavy fraction. So in the previous example, the shape was getting bigger and the length scale factor was 5 over 2, which is like 2.5. In this fraction, it's getting smaller, so the scale factor is a fraction less than 1, which is 2 over 5, which is 0.4. Okay, so that is the length scale factor, part A, 2/5. To get the actual length of side X, so write down length of X. It is quite simply the length scale factor multiplied by the corresponding side to X in the old shape, so times by 15. So 2/5 times 15, and I just need to do a wee bit of numeracy work to work that out. Multiply the top, that's going to be 30 divided by 5, which is going to be 6 centimetres. Final answer. Okay, so I found the length scale factor by using the ratio of the two sides that I'm given, and then I used that to multiply the other length that corresponds to my missing length. Right, let's try one where we have an enlargement, which is in part B. So we have similar triangles, both right angle triangles, and we have the first one, which is 3 centimetres by 4 centimetres, and we have this one which is 8 centimetres by x centimetres. Find the missing dimension x. Now it is more obvious in this case what the scale factor is. Some of you may already kind of be able to work that out. How have we gone from 4 to 8 is quite obvious. So what would x be? But we're going to work through it the same way that I want you to do it every single time. So draw me the triangles, mark on those the information, make sure you have the correct ones in the right spot. So the first bit is to find the length scale factor, and that is the new length divided by the old length. So that the new length of the two that I'm given is 8, and that's divided by 4. So I need to use the two corresponding sides, which I have the actual numbers for. So it's 8 over 4, which is just 2. So that was kind of obvious that we've multiplied by 2 to get from 4 to 8. So therefore, to get the length of x, it's going to be the length scale factor multiplied by the corresponding side to x, which is 3. So that's going to be 2 times 3, nice and easy this time. So again, the answer is 6 centimetres. Okay, so I hope you find that straightforward so far. We are going to look at example 2 now, which is slightly more complicated when we have basically triangles with parallel lines or triangles within triangles. You'll see what I mean in a wee second. Any questions you have about any of this, just ask me as I go along. Send me an email, send me a comment, just whatever is the best way for you to ask me a question, do it. Right, example 2 we're going to go on to, and you'll see what I mean about these triangles within triangles. So, when two triangles have the same 3 angles, then they are similar. Okay, this often happens when we have triangles appearing within parallel lines. It's easier to see the similarity when the triangles are rotated and put side to side. Okay, so what that means is basically from these two diagrams, we are going to pull out the kind of corresponding triangles, the similar triangles, and draw them side by side so that they match up with the corresponding angles. They're rotated the right way, and then we're going to do the exact same as we've just done. Okay, so this is more kind of Nat 5 level style question. So what we've got here is we've got a big triangle which has 36 millimeters down the left hand side here, 40 millimeters kind of along the bottom, and we have a smaller triangle which has x, kind of it's more obvious if I mark that on there, which has x as that length and has 16 millimeters along the bottom. So that diagram is relatively confusing. So what I can actually do is I can pull out this smaller triangle and mark on the information, and then I can do the same with the bigger triangle and rotate them, make sure they're both facing the right way, they're rotated the right way, so the corresponding angles and lengths match up. So that's 40 millimeters down there, and then that's 36 millimeters along the top. So now I have two triangles that are more easy to deal with, really. So the process I need to use to find x is I need to find what the length scale factor is using my 16 and my 40. Now getting them the right way around is crucial. I'll talk about that in a second, and then we're going to use that scale factor, multiply it by the corresponding side to x to get our missing one. So first stage, find the length scale factor. Okay, if we look back to our previous examples quickly and look to what it says here, this is really, really important. It is the length in the new shape divided by the length in the old shape. Okay, the length in the new shape divided by the length in the old shape. So the two ones that we have actual numbers for are the 16 and the 40. That's the two sides, corresponding sides we have numbers for. So it is the new shape length, so new length divided by the old length. By new, it just means whatever shape has the unknown in it. Okay, So the new length is going to be 16, the old length is going to be 40. Okay, you do have a calculator for this. So if you don't have a calculator, if you haven't been using a calculator for those previous examples, you will be given a calculator here. So 16 over 40 though, I will be expected to simplify that without a calculator. They're both in the 4 times table. They're both in the 8 times table actually. So if I divide both sides by 8, I'm going to get 2 over 5, 2/5 from a length scale factor. Okay, so you need to make sure you're fully simplifying that fraction to 2/5. Now, to get your value of x, so length of x, you take your length scale factor and you multiply it by the corresponding side to x, which is the side that is the same, pointing the same way in both shapes. So that is 36 millimeters. So 2/5 times 36. And as I say, you get a calculator for this, so this one is not as easy to do mentally, so let's put it into a calculator. 2 divided by 5 times 36. Okay, so 72 divided by 5, so that is 14.4 millimeters. Okay, so we've taken the diagram, we split it up and found the length scale factor, then found that value of x. Now we're going to do the same thing here, although slightly more complicated to draw these in the same fashion. So we want to draw these out in a second so they're both basically pointing the same way. So I've got one triangle on the bottom with this parallel line here, and I've got another triangle on the top which is similar, but it's been kind of rotated by 180 degrees basically. If you imagine taking that top triangle and just rotating it 180 degrees to the left, it would look the same as the one on the bottom, just a bit bigger. So we're going to start by drawing the one on the bottom, which is going to be here, here, and here, and that is 3 meters, and that is 4.5 meters. And imagine rotating that one on the top. So I've got the long side along there. I've again got that sloping line there and down there. So if I rotated that 180 degrees like that, this side would match up with this 4.5. So that means this is x, that's the missing side. And this side on the right is my 3.6 meters. If you're struggling to visualize that, literally just turn your screen upside down or your phone upside down, whatever, and you should be able to see it better. So find the length scale factor. The 2 corresponding sides we're given are the 3 and the 3.6, so that's the 2 we need for the length scale factor. Then we're going to multiply it by the 4.5. Alright, so we're just doing the same as before. So length scale factor is going to be the new length divided by the old length. And at this point, I'm going to pause and I'm going to let you do it. Now this kind of works out to be funny. So the new length, I'll just show you again. The new length is, so it's 3.6 and 3 that we use. The new length is the one with the unknown in it, so that's this new shape here. So that's going to be 3.6 divided by 3. So that's not a fraction. We wouldn't tend to leave that as a fraction because that is divisible by 3. So it's going to be 1.2. Right, that's just 3.6 divided by 3 in your calculator. That's what you're going to get. What I'd like you to do now is find me the length of x. So the length of x is going to be the length scale factor multiplied by the corresponding side to x. I'm actually going to pause this. I'm going to let you do this. Write your answer in the comments now. I'll give you one. This will only take you 1 minute. So get your length scale factor, multiply it by the corresponding side to x, Write your answer in the comments. Go. Yes, everyone seems to be getting this okay. So it is length scale factor times by 4.5, which is going to be 1.2 multiplied by 4.5, which works out to be 5.4. And yes, thank you, Sam Dalgleish. That is 5.4 meters. So make sure you have the correct units for length there as well.